Hello, good morning, everyone. We're slowly joining in. Let's wait. Only 12 of us, including myself as yet. Not so many, unfortunately. Thirteen. Let's wait a bit. Yes, actually, you are right. So the link itself is not sufficient.
Yes, the link is not sufficient, so I sent the password.
Oh,
to
thank
the
you
chat.
so much. Thank you so much. Yeah, so it helps tremendously. 30 people already in.
Mhm.
Professor, can I ask you a question?
Yes, indeed, yes.
When you calculated I prime, J prime, and K prime for
Topocentric coordinates.
topocentric coordinates, yes. I can't understand how you calculated vector K and vector J, because it seems to me that instead of sine phi, it should be cosine phi, and vice versa. I can't understand how you do that.
Let us recheck that. Yes, we'll recheck that. Okay.
Okay.
Here you mean for J prime?
For I prime and J prime, yes. For K.
For I prime and J prime. Have a look, and I will get back to you just in 1 minute. So we're still waiting for other people to join in. We'll start from that point. We'll revisit it.
Okay.
Okay. Okay, good morning once again. Welcome into our lecture on analytical geometry and linear algebra. We'll start today from the point which we were considering last time, transformation between topocentric and geocentric coordinates using matrix notation. Then we'll do more complex transformations today, including spherical coordinates. We'll discuss what it is, rotating coordinate frames, and general rotations in 3D. In general, we already have all the machinery. We have matrix algebra in order to do it, but the things are technical, so it is worth doing it over and over again to develop the techniques to that end. Okay, so let's have a look. And we once again consider the x, y, z, which are geocentric coordinates, x, y, z, and x prime, y prime, z prime, which are topocentric coordinates. So what we did last time, so let's revisit it. We provided expressions of normal vectors in the new coordinate system. So x, I prime, j prime, k prime are new, and I, j, k are old. We're expressing at this point, we're expressing new normal vectors while old ones, but you will see that eventually we'll arrive at formulas other way around, giving us old x, y, z in terms of new x prime, y prime, z prime. So once again, one of you have asked whether we did it correctly here. So let's say, what is I prime? I prime is a horizontal vector which is parallel to the xy plane because it is pointing due east. So it is parallel to the equatorial plane. So xy is a plane of Earth equator, actually. Okay. So why do we have these coordinates actually? You see, what is our vector I prime? So this is a vector which is projection of a radius vector of our O prime point, our topos, our center of the topocentric system, to the equatorial plane. Now, the I prime vector is rotated 90 degrees compared to that. So the angle between I prime and x is lambda plus 90 degrees, all right? Lambda plus pi over 2. Therefore, cosine of that vector would be minus sine lambda. And the angle between I prime and y is exactly lambda. So we have cosine lambda here. So this seems to be correct. Now for j prime is pointing due north once again. So its projection to the xy plane is collinear with the projection of the radius vector. So it is this one which I'm pointing out right now. But pointing due north, it is actually of opposite direction than the projection of the radius vector. Therefore, it's the absolute value of its projection to the xy plane is sine phi, and indeed, when phi is 0, then j prime is completely vertical, and therefore it has 0 projection to xy plane. When phi is, on the contrary, 90 degrees, pi over 2, then j prime is horizontal, so it has projection being 1. Therefore, its projection on the plane is indeed sine phi, but if we have, you see, for the radius vector, we have just cosine lambda, sine lambda, here. For J prime, we have the opposite direction because, as I said, the projection would be pointing the opposite way. And that's why there is a minus in front, minus sine phi cosine lambda, minus sine phi sine lambda. And it's easy to see that the angle between J prime and K, the vertical Z axis, is cosine phi. Well, the cosine of that angle is cosine phi. Indeed, when phi is 0, then they are collinear and it is 1. When phi is pi over 2, then it is 0. That's why we have those projections for J prime, and projections for K prime are the same as for our coordinates of O prime point, apart from the fact that the radius vector R is in that case 1, because K prime is just a unit vector. So this looks okay. You can easily check that, for example, the dot product of I prime J prime is 0. Once again, you can check that, for example, I prime K prime is 0. So once again, we have minus cosine phi sine cosine lambda. Plus cosine phi sine cosine lambda and 0 here. And finally, once again, I prime K prime is 0. And once again, I prime K prime, which requires most calculations in this case, but it is not very difficult either. For the first two components, we have sine cosine phi cosine squared lambda with minus. For the second one, again with minus sine cosine phi sine squared lambda, and therefore altogether it is just sine cosine lambda with a minus, sine cosine phi with a minus, and then for the third component is sine cosine phi with plus. So that looks, just a second, let me double check here. So sine, once again, we have for lambda, for do we get orthogonality here? Let me double check. So for this we have sine phi cosine 5 cosine squared, sine 5 cosine sine squared. Yes, indeed. So they are orthogonal as well. Okay, so that's fine. We got I prime, J prime, K prime, and let me denote the components of these vectors as A11, A21, A31 that way, and which mean that I prime is expressed that way through ijk, J prime is A12, A22, A32k, and K prime is A13, A23, A33k. Okay, now I will dwell on that point once again. For any geometric vector v, I will explain later on once what it means. It really means a geometric vector which we consider as a directed straight line segment. It would admit a double decomposition. One of them is with respect to ijk, with coefficients obviously being x, y, z, and another one with respect to j prime, I prime, j prime, k prime, with the coefficients x prime, y prime, z prime. That's where we actually stopped at the end of the last lecture. So by considering these two decompositions, multiplying the left-hand side of both, multiplying the left-hand side and the right-hand side of this equality by, for example, I, we would get x on the left-hand side, and we would get on the right-hand side x prime times scalar product, dot product, I prime I plus y prime times dot product j prime I plus z prime, obviously, times dot product k prime I. What are these dot products? I prime I is easy to see from this equation that I prime I is A11. Okay, put A11 here. What is J prime I? J prime I is A12. Okay, we put A12 here. K prime I is, in a similar way, A13. Therefore, the expression for x on the left-hand side is x prime A11 plus y prime A12 plus z prime A13. Okay, similar, exactly same way, I can say that y would be expressed as x prime A21 plus y prime A22 plus z prime A23, and z is expressed as x prime A31, y prime A32 plus z prime A33. Which means that at the moment, please note that we disregard translation of the origins. We're only talking about vector components, vector projections. So in terms of vector projections, and that's important to remember, we can then say that our vector x, y, z would be, looking at the right-hand sides here, just a second, I'll make it easier to see. Yes, looking at the right-hand side, we can see that it is just matrix A from A11 to A33. Columns of this matrix, what are columns of this matrix? Columns of this matrix are precisely our vectors I prime, j prime, and k prime, multiplied by x prime, y prime, z prime, or in a matrix notation, denoting the left-hand side as xi, as we did already, and the right-hand side as xi prime. So we get xi equals to a times xi prime. Now we got formulas other way around, expressing old coordinates through the new ones. Well, almost. What have we not done yet? Any ideas, please? What have we not done yet? In terms of projections, this formula is correct. So we really can say that xi is equal to A times xi prime, where matrix A is this one, composed of column vectors I prime, j prime, k prime. And yet something is missing. Please, any idea?
Translation.
Translation is missing. You're absolutely right. So we would say up to translation, if we really identify the origins O and O prime, then yes. With translation taken into account, it would be xi equals to, okay, it's very easy to see. When xi prime is 0, then we're in the origin of the topocentric coordinate system. So we're really in our point O prime, okay? What are the psi coordinates in this case? They're exactly x0, y0, z0, as defined here. So plus x0, y0, z0. Or we can denote this vector by, for example, psi prime 0, like psi prime 0, because it is really coordinates of 0 psi prime in our original coordinate system. Or maybe it would be more convenient just to denote it as psi 0. No, I think psi prime 0 is more appropriate, actually. Therefore, we get a times psi prime plus psi prime 0, where psi prime 0 is the vector of coordinates new origin O prime in old xyz. So this example, you know, it's probably better to just do it once as we did and remember. So what we do, remember just as a rule of thumb maybe, because otherwise you would need to write those equations for a vector in ijk and I prime, j prime, k prime over and over and over again and derive the translation formulas. So what we did, first of all, in this case, in this particular case, using mostly geometric arguments, so using projections, okay, using projections, we constructed new normal vectors I prime, j prime, k prime in the old coordinate system. So initially it is that way. Initially it is new normal vectors in the old coordinate system. I prime, j prime, k prime expressed in old ones. And we constructed them as column vector and denoted them in a standard way. So the first index is the row number. The second index is a column number. Therefore, column 1 corresponds to I prime, column 2 corresponds to j prime, column 3 corresponds to k prime. So we constructed these 3 column vectors. Then we made a matrix by sticking these column vectors together, one by one, our I prime, our j prime, our k prime, okay, together. And we obtain the matrix A, which is other way around, a matrix of transformation giving us old coordinates y new ones. So now old x, y, z equals to this matrix A times new coordinates x prime, y prime, z prime. And to complete the picture, we need to add translation. And to that end, we add the vector of x0, y0, z0 given by these formulas, which are coordinates of the new origin in the old one. So this is precisely our topos, which means our place, which is the center, the origin of our new topocentric coordinate system. These are coordinates of O prime in the original coordinate system x, y, z. Any questions on that?
Excuse me, can I ask a question about our lab home tasks?
Yes, you can.
In this task, we have some problem where we need to change coordinate system and not basis, and it was giving the coordinates of point O. So I discovered that there is a different formulas and task not the same to change the basis. But can you please explain theoretically, but it's why it is not the same task to change coordinate system and to change basis?
Well, change coordinate system and change basis may or may not be a same task. So you see, changing the basis is really what we have done here. One basis is I prime j I j k, and another one is I prime j prime k prime, right? So when we do a change of basis, then we arrive at this formula without translation. Xi equals to a certain matrix A times Xi prime, as we did. So this is actually change of basis. Change of basis. Looking at our geometric picture, you see in the red, ijk is one basis. Another one is, again in the red, I prime, j prime, k prime. But if we only change basis, then we implicitly assume that our coordinate, our origins are the same. So change of basis is sufficient when we do not care about translations for whatever reason. So it may very well be, for example, in the geometrical example like that, that indeed points O and O prime coincide. Only the bases are different. So we have one coordinate system which is simply rotated compared to the other one, but without any translation. In that case, our coordinate transformation is indeed the same thing as changing the basis. That's okay. But in this particular case, we know that it is not enough. In this case, not only the basis is changed, but also there is a translation between the coordinate systems. And then just understanding what kind of problem it is, we say, okay, apart from changing the basis, we also need to change the origin by translation. And that's why I said changing the basis is almost what we almost all we have to do. But in general, we have to add translation in this case. So it just means that in your home assignment and in our task we have done here, the assumptions are different. In your task, you only need to change the basis implicitly, assuming that there is no translation. In our case, we do know that, yes, there is a translation. Okay?
Okay, understood.
Okay. So, first of all, what are further steps? We got eventually a formula which allows us to express, as we need to do, old coordinates through the new ones, right? So that's what we got here. Now, we want, obviously, the inverse transform. How do we express Xi prime via Xi? Xi prime, in that case, is, as you can easily see, the inverse matrix A times the difference of Xi minus Xi prime 0. So we have coordinates x, y, z of our point. We subtract from those coordinates the coordinates of our O prime and multiply on the left by the inverse matrix A. Now, can you tell me, please, in this particular case, what is the inverse of our matrix A? Matrix A is here. What is the inverse of A? In general, in your tutorials, you have already been doing, I presume, inverses of general matrices, with non-zero determinant. So you already know what, we'll talk about that as well. What is the general inverse of a matrix? But what is the inverse of A in this particular case? Well, first of all, let us recall the definition of what is the matrix inverse.
Excuse me,
Yes?
Professor. Could you turn on the messages from the Telegram, please? It's really annoying.
I'm trying to, but it doesn't stop, unfortunately.
You could just close the Telegram for the lecture if it is
Yeah,
possible.
I'm trying to, unfortunately, yes, I apologize for that, but it is popping up, so let me try to do that. Okay. It might be that it is integrated with the desktop, so if I can't conquer it now, then I promise that, you know, for the next time, I will completely switch it off.
Okay, thank you.
Thank you, because it is not running now, yet it is popping up. I think it is somewhere in the desktop integration. Sorry for that. So, what is the inverse of our matrix A? First of all, let us recall the definition of a matrix inverse. If we have a matrix A, then we can also define, as we did, you remember, a unit matrix. Or also called identity matrix. This is a matrix which has ones on the main diagonal and zeros everywhere. So in a 3 by 3 case, it is very simple. It is just 1 0 0 0 1 0 0 0 1. Okay? And then the inverse matrix is such that, let us denote this identity matrix by I, is such that A times the inverse is equal to our identity matrix. The identity matrix has a property that for any matrix M, M times identity equals to identity times M equals to M, with this type of identity matrix, which has ones on the main diagonal and zeros everywhere. How do we prove this? Using the formulas of matrix multiplication, you remember row by column, you can just simply verify that it is the case for any matrix M. And in this case, although we know that matrix multiplication is in general non-commutative, you remember about that, right? With identity matrix, multiplication is commutative due to this extremely elementary structure of the identity matrix. So Mi equals to Im equals to M for any matrix M. Okay? Now, if we define matrix inverse A to the power minus 1 inverse of A in such a way that A times inverse equals to our identity matrix, then we can very easily prove that in this case, in this particular case, multiplication of a matrix by its inverse also on the left also yields identity matrix. A to the power minus 1 times A equals to I as well. So in this particular case, again, you have commutative multiplication. By the way, how do we prove this from from that. Suppose that A times A minus 1 is identity. How do we prove it other way around? I will leave it for a small exercise for you. If you have any questions, we can discuss it later on. Okay, so what is the inverse matrix in the geometrical sense? We have already seen it in a 2x2 case. It would correspond to the inverse transform. So if the direct matrix was, for example, for rotation at some angle alpha, the inverse matrix would correspond to a rotation other way around at the angle minus alpha in a two-dimensional case. Here it is similar. So if matrix A corresponds to a direct transformation, again disregarding translation as yet. So this is not just a single translation, but you see in general a three-dimensional translation, which moves from one coordinate system to another. Then the inverse of A is the inverse, represents inverse sequence of rotations, which constructs our transformation the opposite way. But in this particular case, when our matrix A is, you remember, orthogonal and normalized, which means that rows and columns are orthogonal to each other, and the sum of squares in each row and column is equal to 1. And in addition, believe me, but you can verify it, what do you think is the determinant of our matrix A?
What?
1. Please check. It is really 1. Okay. Once again, coming from a two-dimensional to three-dimensional case, if we say that matrix A is orthogonal and normalized, so all rows and columns are orthogonal to each other, the sum of squares of each rows and columns is 1. Does it necessarily mean that the determinant of A is 1? Please recall the 2x2 case. Yes, orthogonal. Yes, normalized. Does it really mean that the determinant needs to be 1?
It can be 1, but it's not necessary.
What are other possible values if it is not necessarily 1?
-1.
-1. So actually, it is possible to prove that if our matrix A orthogonal and normalized, then the determinant of A equals to ±1. In this case, we can really say that the determinant of A is +1. You can really check this. So write down, this is a very good exercise for you, write down matrix A, expressing all these Aij coefficients through sine and cosine functions of phi and lambda, as we did, and honestly compute the determinant. You remember the formulas for the determinant for a 3x3 matrix. You will get 1 after collapsing all trigonometrical terms. What would it mean if we got in a similar way a determinant -1 geometrically? Let's discuss from the geometrical point of view. Suppose that somehow we got the determinant -1. So what would it mean?
it would mean, for example, that I prime would point not to the east, but to the west.
Indeed, yes. It would mean that we introduced some kind of mirror symmetry in our coordinate system. So I prime, J prime, K prime would no longer be a right-handed triple. You remember it is a right-handed if looking from the top of the vector, let's say K prime, the shortest rotation from I prime to J prime is counterclockwise. If we point I prime, you're absolutely right. We point I prime to the west, then it would already, the shortest rotation from I prime to J prime would of course be clockwise, and we'll get a left-oriented system. But you know, even without changing anything in those vectors, I prime, J prime, K prime, suppose that we do not even point it to the west or not pointing J prime to the south, we keep them as they are. We can still very easily make our matrix A having the determinant -1. For that end, it is just sufficient to swap a pair of columns. So if instead of I prime, J prime, K prime, please look here, I prime, J prime, K prime, right? If instead of that, we would just, for example, swap the third and the second column and construct our matrix as the column for I prime, then for K prime, then for J prime, then it would have the determinant of -1. Actually, it is possible to prove that if we transpose the columns in such a way that the relative order of the columns is preserved. So for example, it could be, what does it mean, relative order is preserved? For example, the correct order initially is I prime, J prime, K prime. That's how we construct our matrix, all right? If we then do a cyclic transformation and we put our columns, for example, we put J prime first, then K prime, and then cyclically returning to I prime, then the determinant is still +1. If further we put K prime first, then J prime, then I prime, and then finally J prime, then it is still +1. So cyclic permutation of columns does not change the sign of the determinant. How do you prove it? Well, one of the ways you can prove it is simply to verify. Construct such a matrix, compute the determinant, you will see. It is also possible to prove in general that for any orthogonal and normal matrix, a cyclic permutation of the columns doesn't change the sign of the determinant. The general proof, I think you will see in the next semester when you study the general linear algebra. Then there would be lots of theorems you are going to prove about the properties of determinants, and having seen how in general, in the general n-dimensional case, the determinant is constructed, you will see why it is the case. So cyclic permutation preserves the sign. So cyclic permutation of columns, we get +1. But swapping, not cyclic permutation, but swapping any two columns, you would get -1. So cyclic permutation means that your coordinate system still remains right-handed. Actually, if you perform a cyclic permutation of columns, what you only change is the point of view of how you are looking at your coordinate triple, I prime, J prime, K prime. So for example, we said looking from the top of the vector k prime, we need to have rotation from I prime to j prime being counterclockwise. But we can, in a very similar way to say, looking from the top of the vector I prime, we need to see the rotation from j prime to k prime going anti-clockwise again, and so on. Actually, here in this drawing, we're looking not from the top, but from the, let's say, bottom of I prime, and therefore a rotation from j prime to k prime appears to be clockwise here. But if you imagine that you are looking from the positive end of x prime, it would still be counterclockwise, and so on. So these are just geometrical meaning of cyclic permutation of columns in our matrix A is just a different point of view of your coordinate system, but you are still looking from the positive end of each of the columns. Whereas if you swap any of the two columns, it means that you start looking at your system from the negative end of a certain column, and then your system becomes left-handed in that case. So this is some kind of geometric intuition behind that. Okay, and returning to our original question. So the determinant of our matrix is +1. The matrix is orthogonal. So what is in this case the inverse of our matrix, A to the power -1? Well, by analogy with the two-dimensional case, it is A transposed. So in this case, the inverse of A, is A transposed. What is transposed matrix? Can we recall, please?
Row swapped with columns.
Rows swapped with column. Therefore, A11 remains, but then we have A12 in the column, A13 in the first column, right? A21, A22, A23, yes, and A31, A32, A33. The main diagonal composed of A11, A22, A33 remains unchanged, but other matrix elements are just swapped around the main diagonal. That's how we do matrix transposition, actually. How can you prove that A transpose times A inverse, that A transposed is equal to A inverse in this case? Well, you can very easily see this using our general property of what matrix multiplication is. So let us verify that. For example, A transposed times A. Suppose that this is some kind of matrix B. So then we get Bij equals to sum from, let's say, K1 to N. In this particular case, N equals to 3. Then tell me, please, so what it would be? It would be A transposed I what? K A times Kj. But A transposed Ik is the same as obviously A Ki. Therefore, it is sum from K equals to 1 to N, A Ki, A Kj. Now, if I is not equal to j, then due to our normality property, we would have Bij, due to orthogonality property, we would have Bij equal to 0. because rows and columns of our matrix A are orthogonal to each other. So what does it mean actually? AKI times AKJ, and we're summing with respect to K. So K is the row number, I and J are column numbers. Therefore, we take column I, we take column J, any rows, and we multiply column I, taking dot product of column I times column J. As we know that our matrix A is orthogonal, therefore this is 0, okay? And if we take I equals to J, therefore it is the same column, and therefore in this case Bij equals to actually Bii equals to sum from K1 to N AKI squared, and we know that due to the normality property it is 1. Therefore, indeed, if we take A transpose times A, then it is not just any matrix B, it is the identity matrix. For an identity matrix, any element is 0 if it is not on the main diagonal, and on the main diagonal where I equals to J, then the element is equal to 1. Therefore, we can from this conclude that B is indeed an inverse matrix A minus 1. And it is also possible to prove that in general, for any matrix A, for the inverse matrix exists, this inverse is unique. And therefore, if we say that A transpose is such that A transpose times A equals to identity, then A transposed is indeed the unique inverse matrix A minus 1. This is obviously very easy because we are dealing with orthogonal transformations. In general, if the transformations are not orthogonal, you would have to invert the matrix using linear algebra rules by, for example, how did you do it in your tutorials? Please recall. How do you invert a particular 3 by 3 matrix? What did you do?
Find adjoint matrix and multiply by inverse determinant.
Okay, so you are doing this by, first of all, computing the determinant and then using minors and algebraic complements of the minors, right? In the general case. Okay, all right. So there are several ways of how you can do it algorithmically, and this is one very well-known way. Okay, but in this particular case, so if you know that your matrix is orthogonal, and in our example so far we're dealing with orthogonal coordinate transformations, don't even worry about doing those complicated transforms. So if you know that A is orthogonal, then simply use the fact that the inverse of this matrix is equal to the transposed matrix. It's very, very easy in this particular case. Okay, 3-minute break, and we start with the second section. Okay, continuing. Are you ready? Everyone is back?
Yes.
Okay, great.
Yes.
So, a few other important things to remember. What is the inverse of a product of two matrices? A, B, inverse, in general. Well, in general and in an orthogonal case as well. You remember that matrix multiplication is associative, but not commutative. What we can say that AB inversed is other way around, B inversed times A inversed. Why? It is very easy to verify directly. B inversed times A inversed multiplied by AB is the same as, by associativity rule, same as we put brackets differently, B inversed A minus 1A times B. But obviously A inverse A is I, so it is B minus 1 I B. And you can put brackets anywhere here, multiplying by a unit matrix, so identity matrix, retains B, therefore it is B minus 1B, therefore it is identity, and therefore B minus 1, A minus 1 is indeed AB inverse, because multiplying this matrix by AB, we obtain the identity matrix. Okay? In particular, if these matrices, in general, by the way, for a transposition, it is also true that A, B transposed is B transposed times A transposed. This is very easy to check directly. So in the orthogonal case, where transposition means inverse, then these two formulas are also valid. In general, each of them is valid on its own, but for orthogonal case, we really have that inverse is the same as transposition. And in that case, we would be able to say that they are equal. Orthogonal, normal case. But in the general case, each of these two formulas hold on its own. And by the way, from this formula, you can say, I'm showing you, you remember, let's do a small exercise here. Using this identity, which we already know is true, A, B inversed is the same as B inversed, A inversed. How can we prove that if A inversed A is identity, then from this it followed that other way around, A times A minus 1 is an identity as well? How can we prove this? Well,
May I try?
We can multiply first equation by A, and
doesn't quite work, but let's try. You say multiply by A, where on the left probably?
yeah.
A minus 1A equals to, okay, in this case we know that it is A. Okay.
And we can use associativity. So yeah, we can
Yes.
put it in brackets.
Like that?
It is, yeah, like that.
And
we get that is we want to prove because it must be identity matrix.
Well, we don't know what a minus 1 is as yet. And we can't do much. Well, we can actually, but we are more or less on the right way. But immediately we cannot cancel a on the right-hand side, because this means multiplying by a inverse on the right, but we still don't know that a times a inverse on the right is identity.
So we can multiply in the right by a inverse.
Okay, let's do
and get a
a minus 1, a minus 1 equals to a minus 1. Okay, we did. And well, actually, you see, it doesn't help much. We can do a very similar thing, but in a slightly more subtle way. So indeed, let's probably do it like that. So we let us write a. We know that a minus 1 is identity. Therefore, we can say a minus 1, and yes, once again, a minus 1 is identity by identity is identity. Or we can say a minus 1a, a minus 1 due to associativity is identity. We already know by our assumption that a minus 1a is identity. By associativity, right? Sorry, we need to a minus 1 a. Sorry, I probably started, what was our assumption? We multiplied on the left, right? A minus 1, I am implicitly using our assumption in this case, no, not right. So a minus 1a is the identity matrix. Okay, so let's, a minus 1a is identity. What can we say about this? So if we multiply it on, and we already know that this is our formula, a times b inverted equals to b inverted, a inverted. Therefore, what we can say that a minus 1a equals to a minus 1 inverted, because indeed it would be a inverted, inverted, and obviously a minus 1 is a itself. That's easy to see, double inversion. Therefore, if this is the case, what we do, a minus 1 inverted is, okay, which means that a minus 1a multiplied by a minus 1 must be the identity matrix, because one of them is no, other way around. We say the inverse is on the left, therefore, yes, so the inverse is on the left, yeah, that way. Okay, now what can we do? We, if we multiply on the right, so we have a minus 1 a equals to, we multiply by a on the right using this property, therefore we get a, and what we want to multiply by and a minus 1 inverted is identity. No, we're back to the original case. Let us think further about this. So let's this will be an exercise for you. So we see any straightforward transformations like this still do not yield a proof. Okay, we'll return to this point later. Obviously, this identity is true. I invite everyone to think how we can do it. Any straightforward attack, as we suggested, doesn't result in what we want in this particular case. Let's see. What is also important? So we considered the inverse matrices, its connection with the transpose in this case. So let us return to our case of Lambda and Phi angles, which I would like to explore a little bit more precisely. So you remember that we had x, y, z coordinates, and then we would have a lambda angle and let's say a phi angle. And also we would have a radius vector, let's say r. It doesn't necessarily mean the radius of the Earth. And here we would have a certain point x, y, z. So then again, projection onto the xy plane would be of length r cosine phi. Then projecting on x and y would have r cosine 5 cosine lambda, r cosine phi sine lambda, and therefore, as before, we have x equal to r cosine phi cosine lambda, y equals to r cosine phi sine lambda, z equals to r sine phi. That's what we already had. So these are actually transformation formulas between the vector x, y, z and the vector, well, not a vector, but I would say a triple. In this case, it is really not a vector because there is no vector arithmetic applied to it. A triple r phi and lambda. Or if you like to put longitude first, r lambda phi, but let me say r phi lambda. So these are called, these are not Cartesian coordinates. They do not make a vector. So why r phi and lambda do not make a vector? Because there is no vector arithmetic applied to it. It is quite meaningless, for example, to multiply this triple r phi lambda by a certain coefficient k. Okay, multiplying r by k does have meaning of just scaling transformation. So a radius vector is increased k times. But in the same way, at the same time, multiplying the angle phi by a certain factor k and multiplying lambda by a factor k absolutely doesn't have any meaning, any sense. Therefore, x, y, z is a vector. It is just, yes, it is written as a column vector, but it is a vector because it is an element of, as we know, the R3 vector space. But R phi lambda is not a vector. It is just a triple of alternative coordinates, R phi lambda, which are called spherical coordinates. And spherical coordinates are very convenient to use when we really move at the surface of a sphere, for example, at the Earth's surface. In that case, R is constant. If we move along the surface of the Earth, then in our Cartesian coordinates, x, y, z, all three of them are moving. But in the spherical coordinates, in that case, the radius vector is equal to the radius of the Earth, if you remember, if we assume it to be spherical, ideally spherical, and only two coordinates, phi and lambda, are changing in this case. So we're really changing our geographic coordinates on the surface, keeping the distance to the center, which means to the center of the Earth, constant. Therefore, it is R phi lambda as spherical coordinates more convenient in that case. And if we have R phi and lambda, then we know how to compute x, y, and z. But now I would like us to do the inverse transform. If we have x, y, and z, how do we transform x, y, and z into R phi and lambda? We do have x, y, and z, and we need to transform in that direction. What do we do? Well, first of all, how do we compute R if we have x, y, and z?
Using that is equal sum of squares.
It is a positive square root of a sum of squares, yes. We know that by geometric meaning that R is greater than or equal to 0. Therefore, it is a positive square root. If we compute the sum of squares of the left-hand side and of the right-hand side, then it is just R squared. Therefore, R is, you can check, a positive square root of that. Okay, what is phi in this case? Well, first of all, what is the range of phi? The range of values of phi.
From minus p over 2 to pi over 2.
From minus pi over 2 to plus pi over 2, yes. Or in geographic coordinates, we use degrees instead of radians, so we say between minus 90 degrees, which is the south pole, to plus 90 degrees, yes. Which means that, where do we get phi from in that case? From the third equation. Third equation says that sine phi equals to R divided by Z. Oh, sorry, Z divided by R. Okay? And because we know that phi is in between minus pi over 2 to plus pi over 2, so sine phi in that range from minus pi over 2 to plus pi over 2 is monotonically increasing from minus 1 to plus 1. So in that case, sine phi uniquely determines phi, because phi is in this range. Therefore, we can say simply that phi is what? Arcsine of z over r, well, under the genericity condition, if r is not equal to 0, right? Or undefined if r is equal to 0. In the origin, phi is obviously undefined, right? And now, much more interesting thing, let us compute lambda. Any ideas? What do we do to compute lambda? Let us divide the second equation by the first one. We would say y divided by x equals to all other terms, provided that, by the way, provided that cosine phi is not 0, which means that phi is not equal to plus minus pi over 2. Only in that case we can do it. Y divided by x is equal to tangent lambda under this genericity condition that we are not at the pole. Indeed, at the pole, the longitude lambda is not defined in general, right? Okay, it is not 0, so what do we do then? And by the way, under another genericity condition, that x is not 0. Otherwise, the left-hand side is not defined. But suppose that we're under this genericity condition. Okay, what is the value for lambda in that case? What is the range of lambda? First of all.
From 0 to p.
Yes. If we really use the geographic convention for lambda, then lambda is between 0 inclusive and 2 pi not inclusive, all right? Whereas phi may include both actually minus pi over 2 and pi over 2. So that's lambda. Okay, if we are under those genericity conditions, cosine phi is not 0 and x is not 0, then what would be our formula for the value of lambda? Okay, we can start with a simple case. We can say that lambda is equal to arctangent of y divided by x. Again, under the condition x is not 0 and phi is not plus minus over pi over 2. But this is not quite correct. If we consider what is the range of arctangent. So we compute arctangent and we get values which?
From 0 to p.
This is a graph of tangent, which has vertical asymptotes at pi over 2 and obviously minus pi over 2, okay? So, let us draw our coordinate plane xy. So we are looking from top. And by the way, you have probably seen this convention. If we draw a circle and a point inside this circle, this means that z is pointing towards us from the plane of this drawing. It is like a point of an arrow. Whereas if we draw a plus, it means like a tail of the arrow, which means that z would be pointing downwards toward the plane of the drawing, okay? So z is pointing at us. This is x and y, which really correspond to again, a right-handed coordinate system, correct? So in the first quadrant, we have both actually x and y positive, and then for positive x and y, we really get lambda being arctangent of y divided by x between, as we can see, 0 and pi over 2, not including pi over 2, because at pi over 2, we would have, what do we have at pi over 2? We have lambda being equal to, we would have x equal to 0 at pi over 2, and let me move to the original drawing. At lambda equal to pi over 2, x is 0, and this formula does not work, okay? Because we have 0 denominator. So for the first quadrant, this formula works. Now, suppose that we're in the second quadrant, in the second one, in which case x is negative and y is positive, okay? So y over x is negative. Arctangent would give us which value? It would give us a value between minus pi over 2 and 0. Therefore, it would give us a value here. Whereas in fact, we are here. So if both actually y is greater than 0 and x is greater than 0, or I would say y is greater than or equal to 0, then this works. But if y is, let's say again, greater than 0, x is negative, then this formula doesn't work. What should we do instead? It is again arctangent of y divided by x, but what do we change? We would get here, whereas we need to get here. The difference
Plus
pi, correct? And
yes.
obviously tangent has a period of pi, therefore we can, without changing the tangent, we can add pi. Therefore, it is plus pi, okay? This does not, would it work if y equals to 0? No, it would not. If y, yes, if y equals to 0, then we get 0 here, but for negative x, we want pi instead of 0, obviously. So for negative x, so that's correct, and we can put greater than or equal to here as well. Okay, that's for the second quadrant. In the third quadrant, both x and y are negative. And whereas our formula would give us here in the positive quadrant. Therefore, we get lambda equals to, again, arctangent y divided by x plus pi. If y is negative, x is negative. By combining these two formulas together, you see, so it does not depend on the sign of y. So for x being negative, we need to add pi. And finally, if we are in the fourth quadrant, where x is positive and y is negative, what would happen? We would get a value negative between minus pi over 2 and 0, whereas we actually want a value towards 2 pi. Therefore, in that case, it would be lambda equals to arctangent y over x. You guess what?
plus 2 pi.
Plus 2 pi. In case y is negative, x is positive. So unfortunately, this formula does not recombine with the first one. First of all, there is a discontinuity at 0. Y being equal to 0 for a positive x corresponds to lambda being really 0, not 2 pi. 2 pi is not achievable. Whereas if y is strictly less than 0 and x being positive, then we add 2 pi. Okay, that is excluding the case x equal to 0. You see, x equal to 0 is nowhere the case. Now we need to consider this particular case of x equal to 0. What then? If x equals to 0, then what? Let us consider this. So we had x equals to r cosine phi cosine lambda. Y equals to r cosine phi sine lambda. If x is equal to 0, it might be that, for example, I is equal to 0, cosine phi is equal to 0. So r equal to 0 means we're in the origin, okay? In this case, obviously, lambda is not defined. Cosine phi equal to 0 would mean that, what? Cosine phi is equal to 0. We're in the pole. So this is origin, this is pole, north or south. In which case, lambda is again not defined, okay? What else is possible? X might be equal to 0, but in that case, y is also equal to 0. So, case x equal to 0. If y is also equal to 0, it might in particular be that r is equal to 0, but not necessarily. Then what? Lambda is, tell me please, what is lambda in that case?
Not defined.
Undefined. If, however, y is not equal to 0, if y is positive, x equal to 0, y is positive. Therefore, we're here. What is lambda?
Pi over 2.
Pi over 2. If lambda is negative, and therefore we are here, then what?
3 pi over 2.
3 pi over 2. This concludes our analysis. So you see there is a generic case, and there are quite a few specific degenerate cases. We have conducted a transformation between spherical coordinates to XYZ Cartesian coordinates and vice versa, from Cartesian coordinates to spherical coordinates, which is a more complex thing. Actually, this type of transformation to spherical coordinates will be very important toward the end of our course. We'll be studying very seriously the two-body problem of celestial bodies, solar system bodies, for example, moving under the gravitational field of the sun. Our knowledge on linear algebra will allow us, well, plus little bit of differential analysis, which you are studying, you're obviously studying mathematical analysis now at the same time, will allow us to do a very non-trivial stuff. Eventually, by the way, I didn't mention that to you probably yet, we will be able to, in the last 3 lectures of this course, we'll be able to solve the problem of planets moving around the sun under the gravitational attraction, the Newtonian force of the sun, and we'll be able to predict the positions of the planets for any given instant of time using a so-called orbital elements, which is a set of 6 constants, which allows us to actually completely determine the position and shape of the orbit and the motion of a planet along that orbit. And then transformation between spherical coordinates and Cartesian coordinates and vice versa will be very, very important, because on the celestial sphere, we really use spherical coordinate system. We have a system which is called a right ascension and declination, which allows us basically to specify angular position of any celestial body. The distance to this body is of secondary importance. In order to observe it, we need first of all a direction to it. A direction is given by 2 angles. In our case, it is phi lambda for geographic coordinates. All right. For celestial coordinates, the equivalent of phi is a so-called declination. The equivalent of lambda is a so-called right ascension. So declination and a right ascension. And being able to compute declination and right ascension from the Cartesian coordinates will be very, very important. So in your labs, you are going to, I think, implement a numerical procedure which performs the transformations exactly as we discuss them now. We can continue on and on and on, but I think our time is over. Any questions, please?
Everything was clear.
Everything is clear. Wonderful. Thank you very much for attention, and we meet once again next week. Thank you.
Goodbye.
Thank you. Goodbye.
Thank you. Goodbye.
Thank you.
Bye.
Thank you.
Bye.
Thank you.